Primary consolidation is the major part of the total settlement in soil. Primary consolidation is also known as consolidation settlement. It is the settlement of soil layer due to the gradual dissipation of excess pore water pressure under a constant applied load. When analyzing the settlement of a soil layer due to consolidation, we divide the process into two main parts. The first part is the computation of magnitude of settlement, and the second is the determination of the time rate of settlement. For the calculation of time rate of consolidation, Terzaghi's theory of consolidation is used, which involves the determination of coefficient of consolidation. We have discussed Terzaghi's theory of consolidation in detail in our previous video. In this video, we will analyze how magnitude, the amount of consolidation settlement, is calculated. For the determination of the settlement of soil layer, we have two methods. One is based on using the coefficient of volume compressibility, and other is based on using the void ratio of the soil. Let's begin with calculation of settlement using coefficient of volume compressibility. Let us consider a soil deposit of total thickness H0. We wish to know the settlement of this soil layer when the stress on the layer is increased by delta sigma. We begin by considering a small element of thickness delta z at depth z in this soil layer. We know that coefficient of volume compressibility mv is defined as the negative fractional change in volume of soil per unit change in effective stress acting on it. Delta V is change in the volume of soil, V0 is the soil's initial volume, and delta sigma dash or delta sigma prime is the change in effective stress between soil particles. Keep in mind that delta sigma prime is not the change in total stress on the soil, which is delta sigma. It is the change in stress between the soil particles. We rearrange the equation for delta V. We can write the volume as area of soil multiplied by depth in both the sides. Now if we assume the area of the soil layer does not change with the load increment, we can write change in volume as change in its height. This delta H is the change in thickness of the soil layer, which is a negative when soil settles. However, this is, in fact, the settlement of the soil layer. Therefore, we can write it as SC, that is settlement due to consolidation, without any minus sign. For the small soil element that we considered, this settlement can be written as this. For the calculation of the settlement of the whole layer, we can integrate it over the entire depth of the layer. And this is the total settlement of the soil layer. Then there is void ratio method for the determination of the settlement of soil layer. In this method, we consider the soil as two-phase system, which contains only voids and soil solids. Voids may be filled by either water or air. Using the two-phase diagram, we can write this relationship as we consider the area of the soil to be constant. We can write total volume of soil as volume of voids plus volume of solids. We divide both numerator and denominator by volume of solids. We can see this quantity is void ratio, and the quantity in the numerator is change in void ratio. As we know, change in volume of soil is change in its voids. Hence, finally we get this relationship. Rearranging it for delta H. This delta H is the consolidation settlement. To to calculate delta E, that is the change in void ratio of the soil due to the change in pressure on the soil. We can use the plot between void ratio and log of effective stress that we created using consolidometer test results. This test has also been discussed in our earlier video. For the soils that are experiencing the highest load in their history, known as normally consolidated soils, this curve is obtained as a straight line. The slope of this curve is defined as the compression index and is given as this. Rearranging for delta E and removing the minus sign for settlement. Hence, settlement of the soil becomes this. Then for soils that have experienced a higher load in the past than they are currently experiencing, known as over-consolidated soil, we obtain a different type of curve in consolidometer test. This curve is known as a recompression curve, and the slope of the curve is referred as the recompression index, CR. The recompression index can be expressed as this. Hence, the settlement of the soil becomes this. Generally, we encounter soils that have previously been subjected to a load that was later removed, then soil is reloaded with higher load. In such cases, soil's state changes from being over-consolidated to normally consolidated. In this scenario, we need to calculate the soil settlement in two parts. First, when soil was in over-consolidated state, that is, settlement when effective stress reaches from initial value to pre-consolidation stress, and then when soil is in normally consolidated state, that is, settlement from pre-consolidation stress to maximum stress. Up to pre-consolidation stress, the soil remains in recompression phase. Then after that, soil is in normally compression phase. So final settlement is this. As the value of CR is very less, value of this part is very small. So how are we going to calculate the settlement of soil in the field? We begin by collecting the soil sample from the field. We use the sand replacement method for the volume determination of the soil sample. Then we oven dry the sample, which gives us the weight of soil solids only. Next, we calculate the volume of solids using the following formula, where Vs is volume of solids, Ws is weight of solids, which we determined using oven drying, and gamma W is the unit weight of water. Gs is the specific gravity of solids, which is usually around 2.65 to 2.7 for most soils. We have total volume of sample and volume of soil solids. Therefore, we can calculate the volume of voids by subtracting volume of solids from total volume. This allows us to calculate the initial void ratio of the soil layer. Then we perform the consolidometer test on the soil sample to obtain the void ratio versus log of effective stress curve. With this curve, we determine the compression index CC. Finally, we have everything we need to calculate the consolidation settlement of the soil layer using the following formula. I would like to thank my patron for supporting elementary engineering financially. Also, if you think elementary engineering has given you knowledge that's worth something to you, consider supporting this channel on Patreon and get access to the questions and their solutions related to various topics of soil mechanics. Your support will help the channel in its journey of creating valuable content. If that doesn't resonate with you, spreading a word about elementary engineering will also be of great help. Only your love and support keeps elementary engineering going. You can find the links of books and other sources I referred for the creation of this video in the description. Read Calculation of Consolidation Settlement in Soil Deposits at elementaryengineeringlibrary.com. Thank you.